Okay, so today we're going to be looking at tutorial 2b. We have two problems in this tutorial where we consider examples of optimization problems and gain more intuition on how isoquants behave. Question number 7, meaningful and redundant solutions. Consider the utility function, which is a function with two variables, x and y. It is equal to log x plus a half log y minus r1 over 2x squared minus r2 over 2y squared, with rj is greater than 0. So r1 and r2 are both greater than 0 for an agent who enjoys consuming two particular goods in quantities x, y, of which the agent knows overconsumption has a negative health effect at a rate increasing with scale. We need to find the first order conditions. So that means we need to work out the partial derivative of the utility function with respect to x is going to be 1 over x when we differentiate the log minus r1x, and the partial derivative with respect to y is going to be 1 over 2 1 over y dot r2 minus r2y. So we are left with 1 over x minus r1x, and then 1 over 2y minus r2y. Find all the solutions of the first order conditions and decide which one is economically meaningful. Okay, so one of our first order conditions was 1 over x minus r1x is equal to 0, and the other one was 1 over 2y minus r2y is equal to 0. What I'm firstly going to do is times by x and then times by y over here. So we get 1 minus r1x squared is equal to 0, and we get 1 minus 2r squared y squared is equal to 0. So now we get 1 is equal to r1x squared, and here we get 1 is equal to 2r squared y squared. So x is equal to plus or minus root 1 over r1, and y is equal to plus or minus square root 1 over 2r2. These are all the solutions that we have, but we need to find the ones that are economically meaningful. Because x and y are some goods, some particular goods, we cannot consume a negative quantity of goods. So x and y cannot be negative, as we cannot consume negative quantity. Therefore, our solution will be square root 1 over r1 and then square root 1 over 2r2. Moving on to part C, calculate the Hessian at the meaningful optimum. So the Hessian matrix is defined by taking the second partial derivative of x and then the partial derivative of x and then the partial derivative of y and then the partial derivative of y and the partial derivative of x and the partial derivative of y twice. So that is our Hessian matrix. If I again write down the first partial derivatives, I get x minus 1 minus r1x, and for the y I get a half y to the power of minus 1 minus r2y. If I now differentiate the partial derivative of x again, I get minus x to the power of minus 2 minus r1. If I differentiate the partial derivative of x with respect to y, this time I get 0, and that's the same with this, so I get 0 again. And if I do the partial derivative of y with respect to y, I get minus a half y to the power of minus 2 minus r2. Now, we know the meaningful optimum was when we had x is equal to 1 over 1, when we had x is equal to square root 1 over r1 and then y was equal to square root 1 over 2 r2. If I now start subbing these in, when we sub it into here, we get minus 2 r1, so that's going to be over here in our matrix. These two will be 0 and 0, and when I sub this into here, we get again minus 2 r2. So that will be the Hessian. If we look at D now, what do you think is it the type of meaningful local optimum? So what type of local optimum is this? Is it a maximum, minimum, or a saddle point? What we are going to do is calculate a dot the Hessian dot a again, where a is equal to a1, a2. So a1, a2, dotted with the matrix minus 2r1, 0, 0, minus 2r2, and then again dotted with a1, a2. When I do this, I get a1, a2, and then minus 2r1a, and minus 2r2a. And when I dot these two together, we get minus 2r1a squared minus 2r2a squared. Okay, so as a dot h dot a is less than 0, the matrix is a negative definite. And when this is the case, it means that the optimum is a maximum. So this means the optima is a maximum. So maximum. Okay, moving on to 8, production problem. Consider a company that produces some good using a technology that gives it the following output. For a function which has two variables k and l is equal to 10 kl as a function of the labour and capital used. Sketch a number of ice quants and comment on what you see. So what I'm first going to do is write this function and equate it to 10. So we have 10 is equal to 10 kl. When I do that, we get 1 over k is equal to l. So now if I look at this, one of the points is going to be 1, 1. When I put 2 in here, we get 0.5. When I get 4 in here, we get 0.25. And hopefully you can tell that this is a hyperbola. So the curve is going to look something like that. And as you increase output, you should see the curve slowly move this way. So you'd have a number of curves coming like this as output increases. So this way as output increases. So to sketch this a bit more nicely, you would put in a range of values. So you'd do 20 is equal to 10 kl. So you'd get 2 over k is equal to l, and then sub in these values and see what L values you get and start plotting. Moving on, some comments that we can make is the graph is convex. So that just means a mix of labour and capital is preferred instead of extremes. Okay, moving on. Okay, question B. Suppose the wages W and the capital rents are dependent on the demand for labour and capital, like W is equal to WO plus 0.2L and R is equal to R0 plus 0.1K. If the production costs are a function of C, which is a function of K and L, is equal to W, which is a function of L, times by L, plus r, which is a function of k times by k. Then sketch a number of cost isoquants for wo is equal to 1 and ro is equal to 3, and comment on what you see. Okay, what I'm going to do is rewrite this function but sub in everything that we know. So the function now looks like L plus 1 over 5 L squared plus 3k plus 1 over 10k squared. So that's just me summing this and these functions into here. I'm now going to let this equal to 10 just as a random number. So 10 is equal to L plus 1 over 5 L squared plus 3k plus 1 over 10k squared. I'm now going to find different values of L when k takes different values. So let's say when k is equal to 2, we get 10 is equal to L plus 1 over 5 L squared plus 6 plus 4 over 10. And then we get 0 is equal to 1/5 L squared plus L minus 18 over 5. So we're left with L is equal to 2.42 or L is equal to minus 7.42, which I'm going to ignore as it's invalid. So if I plot those points, we get 2 and then 2.4, which is going to be somewhere around here. Now what I'm going to do is when L is equal to 0, we get 10 is equal to 3k plus 1 over 10k squared, which gives us k is equal to 3.02, or k is equal to some negative value, which we can ignore. So we get a coordinate over here, and putting back this coordinate, which is disappeared, we get 2.4 looking over there. And when we sub in k is equal to 0, we get 1/5 L squared plus L minus 10 is equal to 0, and that gives us L is equal to 5. So if I now draw the curve, we get something which looks like that. So that would be one of our cost isoquants. If we change this number 10 to a different number, we'll get various looking isoquants that will take some form like that. Some comments that we can make is as costs increase, the curves will move right and upward. Cool. See, search the relevant cost and output isoquants illustrating the following two situations. There's a maximum output choice at fixed costs, and there is a minimum cost choice at a fixed output. So both of these are saying the exact same thing, pretty much. And all we need to do for this question is draw this curve that we have over here and draw this curve on the same graph. So if I roughly do this, we will get something that looks like that as our cost curve, and then something that looks like that as our production function. So I label this production and this is cost. Because they wanted the maximum output choice at a fixed cost, I've drawn it tangential because that is what will give me that maximum output, and the same goes with the minimum cost choice for a fixed output. So some comments that can be made about this is the cost curve and production curve must be tangents to one another in order to obtain a maximum output at a fixed cost. Moving on. Find the first order conditions for the case where this firm decides to maximize output minus cost and solve for the optimum values of K and L. Okay, so we need to do our output minus our cost. So we get 10k k L minus L plus 1 over 5 L squared plus 3k plus 1 over 10k squared. If I just simplify that, well, expand the minus sign, we get 10kl minus L minus 1/5 L squared minus 3k minus 1 over 10k squared. If I now find the partial derivative of this function, which I'm going to call z, with respect to labour, or L, we get 10k minus 1 minus 2 over 5L. If I differentiate this function, or partially differentiate this function with respect to k, I get 10L minus 3 minus 1/5 k. So those are my first order conditions. So I will write them down over here. If I now solve these two functions simultaneously, so we get 10k minus 2 over 5L is equal to 1, and then 1/5 k minus 10L is equal to minus 3. I'm now going to times this by 50 so that I get 10k minus 2 over 5L is equal to 1. 10k minus 500L is equal to minus 150. Subtract these two so that I get 2498 over 5L is equal to 151. When I solve for L, I get 7552498. And when I sub that back into this equation to find k, we get k is equal to 140 all over 1249. So this would be our local maximum. 140, 1249, and 1755 over 2498. I hope that was useful.